farms in high elevation utilize the cold temperatures to grow strawberry runners and daughters in the nurseries. During the growing phase in a strawberry nursery, excessive and unhealthy leaves and flowers may appear, which will do harm to the strawberry plant, so we need to remove them in time. Removing excessive leaves helps the strawberry plant to save water and nutrients. A proper crop load is also good for germinating, blossoming, and bearing fruits. Removing unhealthy leaves in time is beneficial for the growth of strawberry plants and insect pests prevention. Removing flowers can help the plant concentrate more on using carbohydrates for survival and vegetative growth rather than reproductive growth, and this will make strawberry daughters strong, healthy, and productive. However, current removing tasks are all done by human labor. In order to realize a more sustainable and profitable strawberry industry, this laborious and costly process needs to be automated. Based on this situation, 2021 ASAB Student Robotics Challenge is held, and we are Team Robot Never Give Up from Zhejiang University, offering our solution to this challenge. Our team's advisor is Shangjiang Liu, whose expertise is flexible sensing technology and biological information perception, and there are 4 members in the team. Team leader Hui Zhen is responsible for mechanism design and robot debugging. Fang Lang designed the software system and participated in robot debugging. Team member Qina Yang is responsible for mechanism design and artistic design. Xin Zhang designed hardware system and realized wireless communication. All members majored in biosystems engineering. Hui Zhen, Qina Yang, and Fang Lang are junior students, while Xin Zhang is a sophomore. Our robot's goal is to detect the conditions of strawberry daughters in the nurseries, remove all the excessive and unhealthy leaves and flowers, and send the data to the server autonomously. At the beginning of the task, Arduino will lift the operation mechanism and navigate with help of a gyroscope, while JSON Nano loads the YOLO V5S module and import OpenCV library. Then, JSON Nano will turn on the camera. When the infrared sensor senses the plant holder, the robot will stop and start identifying and trimming. The LED ring will give real-time feedback according to the identification result. This chart shows the control logic of our robot. The robot is equipped with a 16.8 lithium battery. 2 Stabilibot modules change the voltage to 12 volts and 6 volts to supply stepping motors, a servo, and a LED ring. The new VEC changes the voltage to 5 volts to supply JSON Nano, Arduino, a camera, and an infrared sensor. JSON Nano controls the camera, while Arduino controls everything else. In order to better achieve the goal, the mechanism of our robot has been updated for several times. At first, we tried to build a gantry robot because it has a balanced and stable structure, but in order to prevent unnecessary contact with the strawberry plants, which may injure healthy leaves, the robot needs to be expanded. However, during our tests, our first expansion method is very unstable, so we used 2 linear actuators to solve this problem. We also came up with an idea to put the camera in front of the trim mechanism so that the identification task and the trim task can proceed at the same time. But during tests, the trim operation sometimes changed the position of the next plant's leaves, which made the identification results useless. So the camera must be put under the trim mechanism, which means the trim mechanism also needs to be lifted, and we designed our third model. This robot can be expanded in 2 directions, and it needs 6 motors. It works fine, but it is too heavy and may cause soil compaction. Another important disadvantage of this robot is that it costs too much. Therefore, finally we gave up using the gantry system and built a one-sided robot. Surprisingly, this robot is able to finish all the tasks steadily, because the materials we use to make the manipulator is very light. This final robot has a suspended crawler chassis to deal with both bumps and hollows on tough ground, and a 3 degree of freedom cylindrical coordinate type manipulator to provide precise motion for the end effector. To better demonstrate the practicability of these robots, we draw the following table. As you can see, the one-sided robot is better nearly in every aspect. Then, I will introduce how we identify the leaves and flowers and match them with the plant holders. Step 1. Adjust the gamma value to 50 to prevent overexposure. Step 2. Find all yellow leaves and white flowers in sight. Step 3.
Draw an annulus and ignore the leaves and flowers not in the annulus. Step 4. Identify the stems in the center area of the picture and extend them. Step 5. For each stem, draw a sector. Calculate the distance between the stem and every leaf and flower within the sector. Find the closest one and pair it with the stem. Step 6. Record the location of every leaf and flower that is successfully paired. These pictures are an actual example of our identification results. And this is a video of the whole operation. The 360-degree servo we use has the precision of 0.2 degree. It is very light and can provide precise control of the manipulator. As for the marker, we tried different line widths from 3 mm to 30 mm. At last, we choose 12 mm to finish the task. It's wide enough to easily mark the target, but not too wide that it will mark other things. We believe this is a contributing information for the chemical spraying area. We also tried ultrasonic sensor and laser sensor to detect the plant holder, but in our tests, the infrared sensor is cheaper, more durable, and more reliable. The robot now adjusts its direction with the help of a gyroscope. It is precise enough for the competition field. In real nurseries, we plan to add a GPS sensor and realize navigation with these two sensors.
As shown in this real video of a real trial, the robot can accomplish the task perfectly and get 4 scores. The scoring detail is shown in this table.
As you can see, the robot can fit in a 12-inch cube box. The robot's weight is 3.8 kilograms and its contacting area with the soil is 0.014 square meters, which makes the intensity of pressure 2.66 kilopascals. In fact, the robot only needs a 2 degree of freedom manipulator to complete the competition, but we designed the 3rd degree of freedom for operations on real strawberry plants. And here is a simulation of how the robot will deal with real strawberry plants whose stems are at different lengths. For practical application, we believe our robot has following advantages. A. High detection accuracy and strong adaptability under various light conditions. B. High mechanism accuracy to trim real plants. C. Crawler chassis equipped with suspended system have better mobility on tough ground. The hardware is sealed so that it can adapt to the complex agricultural environment. E. Highly modular mechanism makes the robot have many potential functions. F. The robot can be connected to the agricultural Internet of Things. The total cost of our robot is $275.61, and $73.88 is spent for computational devices. At last, we would like to extend our sincere gratitude to ASABE. You provide us with a precious platform to exercise our abilities and expand our horizons. We are also deeply indebted to our advisor, Xianzhang Liu, and all the other teachers who once offered their selfless help and guidance. Special thanks should go to Zhejiang University and ARC Robotic Club. They provide valuable resources for us. Finally, thanks to our families and friends for their continuous support, encouragement, and company. The journey of this ASABE competition will be an unforgettable experience in our lives.